Have you ever wondered how we figure out the path of a planet or design the most efficient car engine possible? The secret is a powerful language, a set of tools made to describe and analyze change itself. And that language is calculus. Now, I know it's got a scary reputation, but forget all that. Today, we're going to open up the toolbox and see how calculus helps us solve problems that honestly seem completely unsolvable. So, let's kick things off with a little puzzle. Imagine you're on a road trip. You have a perfect record of your speedometer reading for every single second of the journey, but you lost the odometer data. You know exactly how fast you are going, but not how far you went. How in the world could you figure out the total distance? Well, this is the exact kind of question calculus was born to answer. All right, here's the game plan. We're going to start by learning how to work backwards. Then, we'll decode the secret language hidden in graphs, figure out how to find the absolute best solution to a problem, and finally, we'll put it all into motion. By the end of this, you're going to have a powerful new toolkit for looking at the world. Okay, let's get into our first tool. It's called integration. The easiest way to think about it is like a rewind button. You know how finding a derivative tells you how fast something is changing? Well, integration lets you take that rate of change and literally rewind the tape to see the original picture it came from. So here's our first challenge. We've been given the derivative of some function. You can think of it as its rate of change recipe. We're also given one single clue. The original function crosses the x-axis at -1. Our mission is to use just these two bits of information to rebuild the entire original function, which we'll call f of x. So, how do we pull this off? Well, first we integrate. We hit that rewind button. Using the basic rules of calculus, we get x cubed plus 9x squared plus c. Now hold on, what's that plus c? It's called the constant of integration. See, when you find a derivative, any simple number just disappears because its rate of change is 0. So when we go backwards, we have this unknown number, c. But we have a clue. We know the point -1, 0 is on our graph. So we just plug those numbers in. X is -1, and the result is 0. That gives us a simple little equation to solve, and bingo, c equals -8. And just like that, we've got our final complete function. Pretty neat, right? Okay, so if integration is like rewinding, finding the derivative is like looking under the hood while the car is running. The first derivative is like the car's speedometer. It tells you how fast the function is changing and whether it's going up or down. But the second derivative, now that's like the accelerator. It tells you if that speed is picking up or slowing down. And this accelerator, the second derivative, it helps us find really important special points on a graph. One of the key ones is called a point of inflection. You can think of it as this one specific spot on a roller coaster track where the curve switches from being a dip to being a hump. It's the exact point of change. And the rule for finding it is actually super simple. If the second derivative is positive, the graph is concave up, which looks like a cup. If the second derivative is negative, it's concave down, like a frown. So that point of inflection, the point where it switches between the two, well, that has to be the exact spot where the second derivative is 0. All right, let's put this new tool to the test on the function we just found. Our job is to find the exact coordinate where this graph changes its shape and then figure out for which x values it's shaped like a frown. And check out how clean this is. First, we get the second derivative, which turns out to be 6x plus 18. Now to find that point of inflection, we just set that equal to 0. A little bit of simple algebra and boom, x equals -3. That's our spot. And for the frown part, well, we just need to know where that second derivative is less than 0. We solve that little inequality, and we find it happens for any x value less than -3. No guesswork, no estimating. Calculus just gives us the answer directly. Now we get to one of the most powerful, real-world uses of calculus, optimization. This is all about finding the absolute best value, the maximum profit, the minimum cost, the strongest material. This is how companies save millions and how engineers build amazing things. It's all about finding that perfect sweet spot, and calculus is the tool that lets us nail it every time. So here's a classic challenge. A company needs to make a can that holds exactly 20 pi cubic centimeters. Simple enough, but the metal for the top and bottom costs more than the metal for the sides. So the question is, what's the perfect shape? What radius and what height will make this can as cheap as possible to make? First things first, we lay out what we know. The goal is to make the cost, C, as small as possible. We have a formula for the volume, which is fixed, and a formula for the cost. But here's the catch. The cost depends on both the radius and the height. And it's really hard to find the minimum value of something when two different things are changing at once. And this right here is the key move. This is the big strategy. We can use that volume formula to solve for the height, h, in terms of the radius, r. Then we can substitute that back into our cost formula. By doing that, we eliminate h completely, and all of a sudden, the cost depends only on the radius. And now we have a problem calculus can sink its teeth into. So just try to picture the graph of this cost function. You know, if the radius is tiny, the can is super tall and costs a lot. If the radius is huge, the can is like a flat plate and costs a lot. Somewhere in the middle, there's a dip, a point where the cost is at its absolute lowest. That's what we're looking for. And here it is, the big idea. At the very bottom of that dip, at that minimum point, what's the slope of the graph? It's perfectly flat. The function isn't decreasing anymore, but it hasn't started increasing yet. Its rate of change, its derivative, is exactly 0. So all we have to do is take the derivative of our cost function, set it to 0, and solve. And when we do that, when we run the numbers, the answer just pops right out. The perfect radius to make the can as cheap as possible is exactly 2 centimeters. Calculus just handed us the perfect design on a silver platter. So far, we've used these tools to reconstruct functions and to analyze shapes. But now, let's really get things moving. The study of motion, which is called kinematics, is basically just calculus in action. And it works exactly like our car analogy. If you have a function that describes an object's position over time, its first derivative is its velocity, that's its speedometer. And its second derivative is its acceleration, that's its accelerator pedal. It's that simple. So let's take a look at this problem. We're given a graph that shows a particle's velocity over time. The question is pretty specific. At what moments in time is its acceleration exactly 0? Okay, this is where it all comes together. We know that acceleration is the derivative of velocity. So when the question asks, when is acceleration 0, it's really asking, when is the derivative of the velocity 0? And what did we just learn about optimization? A function's derivative is 0 at its turning points, at its peaks and valleys. So to find where the acceleration is 0, we literally just have to look at the graph and find the highest and lowest points of the velocity. All right, what a tour! Let's take a second to step back and organize this awesome set of tools we've just put into our problem-solving toolkit. First up, we've got integration, our rewind button for finding a function's origin story. Then there's the second derivative, our secret decoder ring for figuring out a graph's hidden curves. Third, we have optimization, our powerhouse tool for finding the absolute best solution to a problem. And finally, kinematics, where we use all these tools to describe and predict the physics of motion itself. You know, these tools are everywhere, from economics and biology to computer programming and engineering. They're not just about math problems. They're a way of thinking about any system that's constantly changing. So the real question to leave you with is, now that you have the toolkit, what are you going to build with it? What problems are you going to solve?